me introduce Professor Erik Curiel. I'll add something to what Professor Fano already mentioned. So Professor Curiel is an assistant professor at the Munich Center for Mathematical Philosophy, and he's also a senior research fellow at Harvard University in the Black Hole Initiative. And today he will give us a primer on the information loss paradox. Let me just add that Professor Curiel will take clarification questions during the lecture. So if anyone has a question, just write me in the chat and I'll deliver your question. And for full questions and discussions, we will wait the end of the lecture. So we will move that at the end. So that said, I'll just leave the digital stage to Professor Curiel and on you.
Thank you, Mirko. So before I share my slides, I also want to say just a very few words. First of all, I want on a more general note, not on the topic of my talk in particular. First of all, I really want to thank Enzo and Enrico and all the other organizers of the conference. First of all, it's of the summer school. I should rather say I'm sorry. I think it's going to be an absolutely wonderful occasion. I'm very excited about it. As everyone else, I'm very sad not to be in Urbino, enjoying the beautiful scenery, the amazing food, the great coffee, and more than anything, the camaraderie of actually going to sit in a cafe and actually talking face to face. There's no substitute for that. There's a thesis of Plato's is one of the very few philosophical theses I think is absolutely true without qualification. All true philosophy happens in conversation. So we'll try to replicate that as much as possible here. So in that spirit, I do urge you to stop me and ask clarificatory questions. The talk I'm going to give is a little different than the one that I had originally planned and sent the title and the abstract to Enrico a while ago. I'm going to be giving much more today background material, because I feel that in order to really do justice to the subtleties and complexities of the problems we're going to be talking about today, there are several issues about the causal structure of relativistic spacetimes, other kinds of global structure of relativistic spacetimes, some more general principles about both relativity and quantum field theory that are not often discussed by philosophers of physics, but I feel are extremely important to have at hand in order to really have a deeper understanding of what's going on. So I will be running very quickly through a lot of material. For some of you, you'll probably know it all immediately, or you'll already have seen it, and I apologize. For some of you, it will be very new, and I'll probably be going through it so quickly that you won't be able to certainly understand everything, with any sort of real depth and clarity first time around. But I hope even those who've never seen it before and perhaps struggle a little bit to follow will still get the gestalt of the principles and the structures that I'm going to be talking about that underpin all of the problems we'll be discussing. I'll say two more things before I start the talk. I liked very much what Enzo said about philosophy of physics, but there's one point that I want to slightly disagree with him about, and one point I want to strongly agree with him about. The point I want to slightly disagree with him about is that it's not even so much a disagreement, it's more perhaps of a friendly amendment. That it is true that in the second half of the 20th century, philosophy of physics has tended to focus on well-established theories, not physics at the cutting edge. But that actually is not that's not, if you look at the history of philosophy of physics, at people who may not have called themselves philosophers of physics, but who by all reasonable standards were doing what I at least, I think many would consider philosophy of physics. the overwhelming majority of them historically actually did work primarily on cutting edge revolutionary physics. So the straightforward philosophers think about, Bertrand Russell's The Analysis of Matter in 1927. He gave an extraordinary discussion of quantum theory, which had just been put into its final form a year and a half before, and of general relativity, which had been put into its final form only 12 years before. And it's a remarkable book. The works of Reichenbach and Carnap around the same time on relativity and quantum theory. And even I think at least as important, and this is the part of Enzo's comment very strongly, of course, not just to men, is that historically looking back, going back at least to Newton and Huygens, the great physicists, most of the great physicists historically were also philosophers. They engaged directly with foundational questions as they were developing their own revolutionary, cutting edge pioneering work. And much of their pioneering cutting edge work would not have been possible without the philosophical work they were doing in tandem with the more straightforward physics. This is not true only of the very far historical figures, Newton, Huygens, Thomas Young, Gauss, Riemann, Helmholtz, Maxwell, but also around the turn of the century, around the turn of the 20th century forward, Lorentz, Poincaré, Planck, Einstein, Bohr, Heisenberg, Schrödinger, Weil. There's a very, very long tradition of the greatest physicists being deeply concerned with foundational issues. And I'm very happy to say that in the past, say 20 years or so, that has started to happen again. And it started to happen because of the extremely odd circumstance we find ourselves in theoretical physics. Many of the greatest physicists today have recognized that working on black hole thermodynamics, semi-classical gravity, quantum gravity, requires foundational work of a kind that philosophers are uniquely suited to engage in. And so they have been there have been in the past 20 years, many active collaborations and many fruitful collaborative networks built between the theoretical physics and the philosophy of physics communities. And I would even go as far as to say that in the kinds of work that we'll be talking about this week, where theory has advanced so far beyond our experimental reach, and theoretical work consists in very large part of arguments based on principles that may or may not have a little bit of empirical entrenchment, extending those principles into regimes in which they are utterly untested, combining them in completely novel ways. To my mind, there's no sharp difference between theoretical and philosophy at that point. They meld they meld seamlessly into each other. Okay, so I think that's all of the mildly preachy stuff I wanted to talk about. So let's actually get to the talk itself. I will ask also, if you feel comfortable doing so, please turn your camera on. It's so much more friendly to look at a wall of faces, even if you're very tiny, than to look at a wall of black boxes or static images. If you don't feel comfortable doing that, please don't worry about it. Or if you have connection problems and your video doesn't work very well, it's not a problem. But the more people I can see, the more I feel like I'm actually involved and engaged, and not just sitting here like a crazy person talking to myself in this room about black holes. Okay, let me share my slides. Can y'all see that?
Yes.
Okay, good. then let's get started. So as you can see, today's title is a primer on black hole thermodynamics and the Hawking effect, not a primer on the information loss paradox. We may get to the information loss paradox at the very end of today's talk, but I kind of doubt it. There's really a lot of material, as I say, I wanted to cover, and because this is a summer school and not an advanced research seminar, I really want us to have collectively, a shared basis of facts and knowledge that we can rely on and that we can call upon. And that is, as I remarked earlier, that I think is necessary for really diving into the foundational questions that we're going to as deeply as possible. So just to give you a roadmap of where we're going, I'll begin with some rather informal remarks about black holes as a way of life. We'll then dive into some rather more technical material, although I've tried to keep the technical, the real heavy-duty technicalities to a minimum, but there is a minimum of that technical material that must be laid out in order to really articulate the problems with some precision and approach them with some rigor. So I'll be talking about causal structure in relativistic spacetimes, asymptotic structure, the Einstein field equation, and energy conditions, all in relativistic spacetimes. I'll then talk about black hole mechanics and thermodynamics, and I'll conclude with a sketch of the Hawking effect and black hole radiation. So I can't resist starting with an image that I'm confident everyone here has seen, but it's an image that bears looking at. No matter how many times you've seen it before, it bears looking at again. It's such an extraordinary achievement. The human beings have taken a picture of the shadow, the photon ring essentially, and the shadow of a black hole. I could easily give an entire lecture on the methodological and epistemological complexities and complications and difficulties that went into achieving this. The extraordinary engineering and experimentation and instrumentation itself is mind-blowing. But it's an extraordinary achievement. We have the first direct evidence of astrophysically compact objects that, according to our best theories, should be something like a black hole. Makes me happy just looking at it. But let's begin by asking ourselves why black holes matter. Well, first of all, they're incredibly cool. And as a scientist, when I'm wearing my physicist hat, actually when I'm wearing my philosopher hat too, the fact that they're incredibly cool really is a good enough reason all by itself to work on it, because you have to have some fun with your work. You have to love your work. And I love working on black holes because they're just incredibly cool. But at least as important, they're also incredibly weird. But they're weird in an extremely useful, salutary, very illuminating way. They can teach us an extraordinary amount because of several peculiar features they have. They can teach us much about the conceptual structure of general relativity, and as we'll see, about the combination of general relativity and quantum field theory. What they can teach us about, and what I mean by conceptual structure is a rather rich and vague idea. It's the idea of what the theories tell us is in some sense or other physically possible in the world. What the theories tell us are quite general principles that we expect to hold true of all systems that we encounter and study. What those physical principles may tell us about how a good understanding of those principles may give us a deeper understanding of the nature of the world itself. Black holes, because of their peculiar nature as purely gravitational objects, as in some sense, both the simplest and the most complex in different ways, purely gravitational objects, they are the perfect laboratory for exploring the conceptual structure of these theories. Besides their, as has been emphasized rightly in the introductory remarks, besides lying at the nexus of so much of theoretical physics today. And that, in fact, is another reason why black holes matter so much. Black hole thermodynamics is one of the most important, central, and fruitful fields of study in theoretical physics that has already moved well beyond general relativity in and of itself, or semi-classical gravity in and of itself. It turns out that conceptual and mathematical structures that we have identified, articulated, formulated, studied on the basis of studying black holes in general relativity, and when quantum effects are taken into account in semi-classical gravity, these conceptual structures and physical principles are turning up just ubiquitously everywhere in physics. We are finding that the ideas, the methods, the principles are the entities, the structures are popping up all over the place. And thermodynamics, cosmology, statistical mechanics, particle physics, fluid dynamics, condensed matter, quantum optics, on and on and on. And they're now connecting these disciplines in fundamental ways, disciplines that were once seen as largely independent of each other. So black holes, among other important foundational properties, they serve not only practically as a way of unifying large fields of physics, partially unifying large swaths of physics that had previously been, we had thought, independent from each other, but also from a philosophical point of view, they allow us to try to study and get a grip on what it means for different areas of physics to be unified by the study of physical systems, of a single type of physical system. I honestly can't think of another example of this in the history of physics, where a type of physical system that was identified, articulated, studied in one very particular discipline, in one very particular field in physics, turned out to ramify into almost every other branch of theoretical physics. I can't think of another situation like this in the history of physics. That by itself deserves, I think, attention and study. They're also widely considered to be the best source of clues to what we hope will be a more fundamental theory of quantum gravity. And that is because, as I intimated earlier, they are in a sense the simplest, non-trivial, purely gravitational system to try to quantize. And in fact, I'll put that aside. I'll get too far afield to go into. I'll simply say that what I mean by purely gravitational here is that almost all of our best exact models of black holes appear in either vacuum or electrovac spacetimes, either spacetimes that have no matter whatsoever, where the stress energy tensor is 0, or spacetimes in which the only matter is a Maxwell field. Turns out Maxwell fields are well enough behaved that, in a certain sense, they fit with the spacetime geometry so comfortably and so accommodatingly that their presence doesn't screw things up too badly the way that the presence of other matter makes things extraordinarily more difficult. So when I say that a black hole is a purely gravitational system, I really mean it's a physical system that in some sense or other is composed simply out of combinations of features of space-time geometry itself, with no material, no input or constraint, no input by or constraint by what we can, I guess, we'll call ponderable matter, ordinary matter, perfect fluids, elastic material, plasmas, cosmic rays, anything treated by the same model of quantum field theory. Also, they're considered the best source of clues to a more fundamental theory of quantum gravity, because their laws mix dependence on and independence from the Einstein field equation in a funny way. So we get access, in a sense, both to the pure kinematics and to the dynamics of general relativity in studying black holes. I won't say more about what I mean by a mix of dependence on and independence from the EFE, because I'll say a bit more about that with some precision later on in the lecture. And the black hole thermodynamics itself, because it's now almost universally agreed that we should take seriously the idea that black holes are, in some sense that's not entirely clear, thermodynamical systems, just exactly, like this cup of tea. Although I couldn't, I suppose, pick up a black hole and take a sip from it while giving a lecture. So it's not exactly like this cup of tea. But thermodynamically, we think it is more or less exactly like this cup of tea. And just as in the 19th century, study of the thermodynamics of ordinary mesoscopic bodies, like this cup of tea, gave us the greatest, the strongest, most powerful, and most helpful evidence to investigate the underlying microstructure of matter, to develop the atomic theory, ultimately to develop the quantum theory by the use of the statistical techniques of physical mechanics. The hope is that by studying the thermodynamics of black holes, we will, in the same way, gain indirect access to the micro degrees of freedom and their dynamics of whatever quantum entities underlie classical space and structure. That is, of course, at this point, I would say, a dream that, if realized at all, will be realized only not anytime soon. I'm far more skeptical about the prospects for immediate success of quantum gravity than I think, as we'll see, Dan Harlow will be, I suspect. So perhaps it's good to have both points of view. I guess I should also say something that I just realized as I've been giving this talk, as I've been giving this lecture, just occurred to me. So far, I'm talking almost entirely about general relativity and space-time theory. And there are two reasons for that. One is autobiographical, and one is, in fact, philosophical. Autobiographical because I was raised on general relativity, so to speak. I was trained by two of the greatest physicists of general relativity of the 20th century, Bob Geroch and Bob Wald. And my philosophy advisors also are two of the greatest philosophers of physics on relativity theory, David Malamud and Howard Stein. So starting from grad school, I had general relativity beaten into me on a daily basis. Although beaten makes it sound like it was unpleasant, but it was very pleasant. But so I know prejudices towards, perhaps a nicer way of saying it is, I have deep predilections for general relativity in physics. But of course, Bob Wald is also one of the great formulators and developers of quantum field theory and curved space-time and semi-classical gravity. So I got some of that as well as a young researcher, and that has certainly been my path in the past several years studying that field, quantum field theories on curved spacetime, the framework within which black hole thermodynamics is formulated. So, as I say, that's perhaps an autobiographical reason why I focus so much on general relativity, but also because I have a very, very strong feeling, which I cannot give you a sustained, powerful argument in favor of, but which I nonetheless think is sound and I hope fruitful, that entering this field of study by way of general relativity is a very useful way to begin thinking about and studying these issues. Because for better or for worse, we don't know how to do physics without, at this point, right now in our current epistemic state, we don't know how to do physics without assuming some kind of underlying spatiotemporal structure. There's extraordinarily interesting work going on right now by several really smart, thoughtful people trying to develop frameworks in which to do physics without assuming underlying spatiotemporal structure. But at the moment, they're entirely speculative, very much incipient, have not made any, have a very difficult time dealing with even modeling the simplest of physical systems in any kind of detail. But they're incredibly useful conceptually, just as proofs of concept to see how far we can get without trying not to assume from the start spatiotemporal structures. But right now, to do physics in any kind of recognizable way that actually makes or has the potential of making real contact with the world, we have to have a foundation of spatiotemporal structure. We don't know how to do physics by starting with quantum field theory and nothing else, but we do know how to do physics by starting with general relativity and nothing else. And that is the non-autobiographical reason why I am emphasizing so much as an entree into the subject, general relativity, as opposed to the quantum field theory, which we'll get to later on. Oh, there we go. So they're cool, they're interesting, they're important, they're clues to quantum gravity, but what are they? Now that may seem like an odd question. Surely we all know what a black hole is, and perhaps it's the complement to the causal path to future null infinity. I'm sure all of us, if put on the spot, could just roll that off the tips of our tongues with no problems whatsoever. And we all know exactly what it means. But actually, there's a great deal of disagreement in the physics world, the broader physics world, about what a black hole is. And disagreement is perhaps the wrong word, because it's not as though people are actively arguing about it. It's rather that, as it turns out, in different disciplines in which black holes play an important role, it turns out that different ways of thinking about them are the most fruitful and have the most salience to the central important problems in the field. And I first realized this when, at conference after conference, talk after talk, I had the experience of seeing, eminent, influential physicists arguing with each other over very basic points, seemingly not being able to understand each other. And I finally diagnosed the problem that they simply meant different things by black hole, but they didn't realize it. They were using the same word, black hole, but they had very different conceptions and ideas about what that meant. And that has led, and still does lead, to a great deal of confusion in its entire field, in both physics and in philosophy of physics. So it's actually worth, from the start, canvassing all the different things that people have meant, might mean, try to mean, want to mean by black hole, And it's, I can't resist preaching a bit here. Also, as an object lesson in philosophy, in one of the most common pitfalls in philosophy that I have seen in both in my own personal career and reading the historical grades, philosophers, for whatever reason, tend to fetishize words. They get really hung up on the term black hole, and when someone else says, for instance, when they're in discussion and someone else says black hole, they assume they know what that word means, and they fixate on it. They assume that there is a canonical, natural, essential meaning to the term, and that everyone more or less even agrees on it, if they don't use it. Everyone agrees that there's some essential meaning to the word. It's a kind of degenerate Aristotelianism that still deeply infects the field. But it's always much more important than the words people use are the concepts they have in play that they are trying to express with the words. So don't get hung up on words in philosophy. Try to figure out what the concepts are behind the words. A lot of confusion in physics about black holes would be cleared up if a lot of physicists took that lesson to heart. So, God damn it. Why is this not working? There we go. So let's look at how the idea of black holes plays out in several different fields. In astrophysics, the core concepts, I should also say, I'm not going to say what physicists in these fields define a black hole to be, because physicists have very different ideas about what a definition means than a philosopher does. To a philosopher, a definition is a logically precise statement of something like necessary and sufficient conditions that something must meet in order to be a certain kind of thing. That's not how physicists use the idea. They tend to have very kind of broad and loose ideas about things that they focus on different aspects of as the work at hand requires. So rather than saying how astrophysicists define a black hole, I'm going to tell you what the core concepts are that astrophysicists tend to use. And this table I've collected from reading many books and papers on many different subjects in each of these fields, talking to physicists, both theoreticians and experimentalists where relevant. There aren't very many experimentalists in mathematical relativity, which is a shame. I think mathematical relativity would be a much more interesting field if there were. But by talking to many theorists and experimentalists in all these fields about what they thought a black hole was, and extracting from all of this what seem to be the most common central ideas that recur again and again. So for astrophysics, in astrophysics, a black hole is essentially it's a relativistically compact object. In other words, it's a very dense object, such that one cannot ignore relativistic effects in its neighborhood. It's really quite shocking. I think when you first learn astrophysics and you really get into even the cutting edge of today's astrophysics. 99% of astrophysics is done using Newtonian gravity. You almost never need to use general relativity in astrophysics. So the fact that black holes actually require astrophysicists to use some of the more highfalutin physics makes these objects very significant for them, even if only epistemically. So for astrophysics, it's a relativistic compact object. It's a region, in some sense, it's a region of no escape. That idea is not always very clear in the context of astrophysics. We'll talk about that later. And it's an engine for enormous power output. We think that black holes, power the quasars at the center of ancient distant galaxies. In classical relativity, and by that I really mean the theory of general relativity without any input from any quantum theory, as developed initially by Einstein in 1915, elaborated by Weil, Eddington, Singh, up through the golden age, renaissance of relativity in the 50s and 60s, Penrose and Gauroch and Hawking. And in classical relativity, a black hole is the complement of the causal boundary of the past, the future, null infinity. It's the boundary of that complement is the event horizon. I'll explain what all those terms mean in a moment. Sometimes, though, classical relativists also use the apparent horizon, not the event horizon, as the definition of a black hole. And the apparent horizon is related to, but different from, an event horizon. It's a more localized object than the event horizon. And they sometimes use a more generalized quasi-local horizon, like Hayward's trapping horizons, or Ashtekar et al.'s isolated horizons. In mathematical relativity, especially among more pure mathematicians, they tend to use, for various reasons, primarily having to do with technical ease and technical tractability, they tend to use the apparent horizon and the attendant singularities that appear at the center of ordinary black holes, standard black holes, as the definition. In semi-classical gravity, the concepts for black holes are both the same as in classical relativity, but now there's another one that's often used. It's a thermodynamical system that is in some sense one of maximal entropy. In quantum gravity, depending on the framework, it's a particular excitation of a quantum field, it's an ensemble or a mixed state of maximal entropy, or there's simply no good definition to be had at all. So, Andy Strominger, one of the godfathers of string theory, in one of his more relaxed moments, admitted to me that in his heart of hearts, he thinks there is no good definition of a black hole in string theory. And in analog gravity, it's a much more practical definition. It's a region of no escape for a finite time that is long compared to some characteristic time of the analog system at issue. And same for low energy modes. It's a region of no escape for low energy modes, with low as compared to some characteristic energies. And if you look at and think about all these core concepts, and think about all the different properties that they respectively, separately, and collectively attribute to what they want to think of as a black hole, I will give you a list, a rather long list, of all the different properties that all these different core concepts attribute. So these are the different properties one may demand of a black hole if one is using any of those core concepts in any of the different fields. It's something that possesses a horizon that satisfies the four laws of black hole mechanics. It possesses a locally determinable horizon in some sense, say an apparent horizon or a quasi-local horizon. It possesses a horizon that is, in a suitable sense, vacuum. The entire system is vacuum itself with a suitable set of symmetries. It defines a region of no escape in some suitable sense for some minimum period of time. It defines a region of no escape for all time. It is embedded in an asymptotically flat space-time. It's embedded in a topologically simple space-time. It encompasses a singularity. It satisfies the O'Hare theorem. It's the result of evolution from initial data satisfying an appropriate Hadamard condition. Continuing, it allows one to predict that final stable states upon settling down to equilibrium after a perturbation corresponds in some relevant sense to the classic stationary black hole solutions, Schwarzschild, Kerr, Reisner, Nordstrom, and Kerr-Newman. It agrees with the classical stationary black hole solutions when evaluated in those spacetimes. It allows one to derive the existence of Hawking radiation from some set of independent principles of interest. It allows one to calculate an appropriate limit from some set of independent principles of interest. An entropy that accords with a Bekenstein entropy, i.e. it's proportional to the area of a relevant horizon with corrections of the order of h bar. It possesses an entropy that is in some relevant sense maximal. It has a lower bound on possible mass. It is relativistically compact. Now, different subsets of these properties are used in different contexts and different investigations, often in the same field. But if you take the entire list that I gave, I guess probably around, somewhere around 20, 25 properties that I listed, they're jointly inconsistent. There are several pairs on there that cannot jointly be true, that cannot simultaneously be true of the same physical system. Well, what that means is that there is no definition, no single definition of a black hole that can accommodate all the actual uses of the concept as it is deployed in contemporary physics. So we already see that there are some serious methodological and epistemological and possibly, depending on taste, ontological problems here. And here's just a small taste. In event horizon, the classical definition of an event, so whenever I say event horizon, I mean the classical definition, the boundary of the chronological past of future null infinity. And again, don't worry, I'll tell you what that means exactly in a bit. The event horizon is global in a certain sense that makes a lot of physicists uncomfortable. And it's global because it makes implicit reference to all future time. One of the common rough intuitive ways of describing a black hole is it's a region such that once you enter, you can never escape, you can never leave. But that modal qualifier, that temporal modal qualifier never, in fact, makes reference to all future time. So in order to know the region of space-time is a black hole, one has to, in fact, know its entire future dynamical evolution to make sure that nothing that entered ever comes out. That fact, this global feature of black holes, and also the fact that, in a sense, there's nothing locally distinguished about an event horizon, means that no local measurements can ever determine its location, much less whether there is one. We all could be sitting right next to an enormous black hole, a black hole whose Schwarzschild radius is larger than the Hubble radius of the visible universe. Well, we couldn't be sitting next to it because event horizons move at the speed of light. But there could be an event horizon right now passing through speed of light for some enormous, some truly enormous black hole. We would have no idea. We could have no idea. There is nothing locally distinguished about an event horizon, which is incredibly weird. Indeed, our universe is not asymptotically flat as you go far away in any direction out towards infinity. So we think you always find matter. There's always curvature. The universe is not a little isolated island of matter with empty space stretching out forever, getting flatter and flatter and flatter the farther away you get. But it's an asymptotically flat space-time that the event horizon, the classical notion of the event horizon, is defined. So our universe, there's a sense in which our universe can't have anything like an event horizon in a classical standard sense. So the definitions used in classical relativity cannot match those in astrophysics. And yet all properties of black holes, all theorems that astrophysicists in fact do rely on in their work, assume the existence of an event horizon. This raises an extremely interesting question about idealization, because clearly the classical notion of a black hole is an idealization. And that's what a physicist will say. Well, yeah, the real universe doesn't have an event horizon, but let's look. For all practical purposes, we are a future null infinity with respect to M87. So it's a good idealization. Don't worry about it. Well, I think we should worry about it. I think we should ask ourselves, in what ways is Sagittarius A star, the black hole, the supermassive black hole we think that resides at the center of the Milky Way, how is Sagittarius A star similar to, and how is it different from a Kerr black hole, the standard exact space-time model, solution to the Einstein field equation, that is what we use to model astrophysically real black holes. And there are even more deep and interesting epistemological and metaphysical problems developing here, such as how empirical content of theories gets fixed when we have no direct observational or experimental access to systems. Although as the Event Horizon Telescope picture I put up in the first slide shows, we are very, very slowly and very gradually and somewhat shallowly, but still remarkably starting to ameliorate that situation. Nonetheless, almost everything I'm going to be talking about today with regard to black holes, we have zero experimental or empirical access to. So how is it, and yet we still think that our theories about black holes have empirical content? How can that be when there's no experimental, there's no contact with empirical observation whatsoever right now? And again, what then can appropriate semantics of theoretical terms can be? Given all the different ways in which the concept of black hole appears and is used in physics, is there a consistent ontology across fields, disciplines? So there's an abundance of rich and deep problems and questions here, and that sadly we just don't have any time at all to go into any of it now. But these are the kinds of problems and questions I want you to have in the back of your mind as we're talking about, as we really get into the subject of the lecture, which I realize I've been talking crap now for almost 40 minutes and I still haven't actually gotten to. So let's actually see if we can now start talking about stuff closer to the subject of the summer school. So we will now try to be a bit more precise, laying down some definitions and stating some theorems to give us, as I intimated earlier, a shared epistemic platform to hold on to when the physical winds start to blow rough and the metaphysical grounds in ceaseless turmoil seas. Because we're gonna be walking through some stormy weather and on some rather shaky ground very, very soon, and having in hand some precise, comprehensible definitions and results will be extraordinarily useful to help us keep our bearings. So let's start with causal structure. So causal structure, the causal structure of a relativistic spacetime is, roughly speaking, all the properties of that spacetime that are encoded in and can be defined by the structure of the null cones, of the light cones, of the distribution of the null cones and light cones in the spacetime. How the null cones expand and contract and twist in relation to each other as one moves from point to point throughout the space-time. So probably the most basic and causal property we'll be worried about today is we'll say that a space-time is temporally orientable. So yes, I'm guessing everyone knows the notation I'm using here, but just in case not. So can you see my cursor moving around?
Yes.
So a space-time, per M, script M, is an ordered pair consisting of a four-dimensional Hausdorff connected manifold with GAB, a Lorentz metric on it. Now, for those who are a little persnickety about technical details, you may have noticed I didn't add paracompact in describing the manifold. Well, there's no need. A manifold has a Lorentz metric only if it is paracompact. So a space-time is temporally orientable if there exists a continuous time-like, perhaps I should have said continuous everywhere non-zero time-like vector field on it. Equivalently, if one can choose one lobe of the null cone as the future one consistently over the entire space-time, and a temporal orientation of such a choice. So a temporally orientable space-time is one in which one can consistently distinguish past from future everywhere in the space-time. And from here on, we assume every space-time we deal with is temporally oriented and temporally orientable, and a choice of orientation has been made. So you might wonder how it is that space-time could not be temporally orientable. It's actually very easy to come up with rather trivial examples that are artificial, but give you a sense of what the concepts are. And perhaps I should say that in the study of causal structure, the examples are everything. The examples give life. There are numerous definitions that are really quite subtle, and sometimes really require a good hard thinking about to distinguish one definition from a very closely related definition. For instance, the examples that really give the subject life and allow one to really grasp the definitions and see how they all relate and hang together. So I don't know why. There we go. So here is because I totally suck at making graphics, I have stolen a lot of my images from the magisterial essay, Global Space-Time Structure by Gierotz and Horowitz from the 1979 collected volume edited by Hawking and Ellis, General Relativity, a Centenary. No, it's Einstein, General Relativity, Einstein, a Centenary, that's it. So on the left-hand side, so these are the light cones. So we just represent the metric very schematically by drawing some of the light cones to give you a sense of how the metric changes from point to point. And here's the light cones are all consistent with each other. Let's say I choose the top one as the future. Well, I can move that around. That's the future. Move it around. That's the future. Move it around. That's the future. Move it back around, and return to the same definition of future. So I can consistently define future around the entire space-time. In this space-time, as I travel around the manifold, the light cones rotate. So here, if I choose this as future, and I travel around, that's future. I travel around, that's future. I travel around, that's future. I travel around, and I return. I find that I want to call future the opposite lobe of the null cone to the one I started with. There's no consistent way to define what I mean by future globally. This is not a temporally orientable spacetime. And we will not worry about these things because they are, in a sense, too pathological to really do much with, which is an interesting fact in and of itself. This illustrates very nicely one of the fundamental lessons of this entire field, which is that global structure has an extraordinary, tremendous, and deep impact on even local features and conceptual features of a space-time. So some definitions: fix a space-time with a couple of points P and Q and some subset, some non-trivial subset S of M. Then the chronological future, I plus P, is just a set of all points that you can reach from P by a future-directed time-like curve. The future J plus of P is the same, just substituting causal curve for time-like curve. We say 2 points are time-like related. If one is in the causal path, if one is in the chronological future of the other. We say they're causally related if one is in the causal future of the other. A closed time-like curve is a time-like curve that intersects itself. And by traveling in the future direction continually, you can return to your original space-time event. A closed causal curve is a causal curve that intersects itself. We say that the space-time satisfies chronology or is chronological if it has no closed time-like curves. And we say it satisfies causality or it is causal if it has no closed causal curves. I'm assuming, of course, here a very basic modicum of knowledge. I'm assuming everyone knows what a time-like vector is, what a space-like vector is, what a null vector is. I wish I could give an entire course on the foundations of general relativity, but don't have the time. So I hope everyone is following so far. And of course, all the relevant definitions can mutatis mutandis be formulated for paths. and we used the indicator minus rather than plus for that. So the chronological past of a point, I minus P, is a set of all points such that it can be reached from P by a past-directed time-like curve from P. And some of the fundamental properties and results about these definitions are that the chronological future of a point is always open. I think it's fascinating. That open, I mean open in the topological sense. I think that there's something very deep about that fact, but I have no idea what it is. I would really, really like to understand it, what this means physically. You might be tempted to say, well, it's open because what that means that it's open is that there's an upper limit to velocity, the speed of light. There's a boundary to the chronological future. But that can't be right, because the future of a point in Newtonian spacetime is open as well. So the fact that the future of a point is topologically open is a fact that runs very deep in our idea of spacetime, and I have no idea what it means, but it's of absolutely fundamental, crucial importance. It's not exaggeration to say essentially every single theorem we're going to talk about today wouldn't work if the chronological future weren't open. The causal future, which crudely speaking is the chronological future, the interior of the future light cone, plus the boundary, all the null curves you can draw starting from the point. So the complete null cone is not necessarily closed. You might think topologically closed. You might think it is, but it's actually very easy to construct examples where it's not. Like just delete a point from Minkowski space. Draw a null geodesic from where that point would have been back to some point to its past. Consider its causal future. It's easy to see that causal future is not a closed topological closed set. If the causal future is closed, and the causal past also is closed for every single point, then we say that the spacetime is causally simple. The condition of causality implies chronology. If there are no closed null curves, then there are no closed time-like curves. But chronology does not imply causality. You can have closed null curves. Wait, I'm sorry. I got it backwards. Causality implies chronology. So if there are no null curves, then there are no closed null curves or no closed time-like curves. But chronology does not imply causality. You can have closed null curves without having closed time-like curves. And just some pictures, because pictures are really great in the study of causal structure to really help you get a grip on what's going on. So this picture shows you, in effect, why the chronological future is topologically open. For any point in the chronological future of P, the Q, I can go back a little. Since it's in the chronological future, I can connect P and Q by a time-like curve. I go a little bit to the past on the time-like curve, to some point Q naught, and then the chronological future of Q naught is entirely contained in the chronological future of P, and it acts as a neighborhood of Q, as a topological neighborhood of Q. So the chronological future of P is open. Here's an example of a spacetime that satisfies chronology but doesn't satisfy causality. So it's Minkowski spacetime that we have kind of chopped into a slice, identified the end, so it's a cylinder, and we've rotated it in 45 degrees. So if you follow this, these are the light cones. If you follow the null geodesic of this guy around, it clearly comes back on itself. So there are closed null curves, but the slightest deviation into a time-like curve will just wind around forever and will never come back to itself. So there are no closed time-like curves. Some more definitions. S is achronal if a subset of the manifold S is achronal if no two of its points are time-like related. And it's important to realize that a subset, say a hypersurface of a spacetime, can be space-like. All vectors that are tangent to it are spatial vectors or space-like vectors. and yet not be achronal. I'll show you an example in a moment. Then the future domain of dependence is defined as for a closed achronal set S, the future domain of dependence, written D plus S, is a set of all points such that every past inextendable causal curve through P intersects S. So if you have this surface S, there's a point P to the future, but such that every causal curve running backwards from P necessarily hits S, then P is in the domain of dependence. And crudely speaking, intuitively speaking, what that means is every single thing that can causally influence P, well, it must traverse some causal curve to get to P. It had to register on S. It had to hit S on its way to P. So all the information that we can possibly use to predict or determine the state of P, it exists on S. That's why we say it's the domain of dependence. Again, I'll show you a picture in a moment. The picture is much easier to get, I think. A Cauchy surface, or sometimes called a Cauchy slice, is a closed achronal S such that the domain of dependence is the entire spacetime. So in other words, if I fix all the data on a Cauchy slice, then that determines the state of every point in the spacetime to the past and future of the set. Say a spacetime is globally hyperbolic if it contains a Cauchy slice. And a Cauchy time function is a mapping from the manifold to the real numbers such that its level sets, the pullback of a real number, are Cauchy slices. So I'll explain what all these mean and how they all fit together in a moment. So here's an example of a space-like manifold in Minkowski spacetime, which is not achronal. So it's kind of like a spiral ramp in a parking garage. It's everywhere space-like because it never tilts up enough to enter into the null cone, but it just keeps on gradually spiraling up, so that there are 2 points on it that in fact are in time-like relation to each other, even though the whole thing is space-like. And here's a picture of the domain of dependence of a surface S, say in Minkowski spacetime, with its point removed. So every single point in D plus of S is such that if I start here, every causal curve, let's say I start at the plus, so I have a good fixed reference point. The point in D that is right at the plus, every causal curve to the past of the plus sign hits S. So everything that can possibly causally influence that point passes through S, registers on S. Don't worry about this boundary right now. We'll talk more about that in the next lecture. So we need some fundamental results about globally hyperbolic spacetimes. This is a absolutely fundamental theorem due to Goroch in 1970. So a spacetime with a Cauchy slice, so a globally hyperbolic spacetime, is such that one, S is always an embedded topological submanifold of M. And from here on, without loss of generality, we can assume it to be a differentiable manifold, not just a topological submanifold. M has a very simple topological structure. Its topology is the topology of the slice S cross R. One way of thinking is that the manifold M is foliated by Leibniz diffeomorphic to S. That defines a Cauchy time function on M. So if this is our space-time, then it's completely, then you can think of it as being filled by Cauchy slices stacked on top of each other, each one associated with a definite moment of time. Every inextendable time-like curve intersects S exactly once. M is causally simple. All the causal futures and past are closed. M is the disjoint union of the chronological past of S with S and the chronological future of S, so it can be decomposed in a very elegant and useful way. And finally, all the causal diamonds. For any two pairs of points, if I take the causal past of one and the causal future of the other and intersect them, so I get a diamond shape, that set is topologically compact for everything. So let's say a little bit more about what all this technical machinery means, because mathematics in physics is only as useful as the conceptual picture and conceptual understanding you have that goes along with it. You can be the most virtuosic mathematician in the world and prove theorem after theorem about Lorentz geometry. But if you can't tell me what the theorems mean physically, I don't care. This is even though this sounds like, and is, I suppose, a very mathematically technical theorem I just stated, it has very clear and fundamental and important physical content. So as I said, the future domain of dependence is a set of all points such that a complete specification of physical data on the set S that we're considering the domain of dependence of determines the state of space-time at every P in the domain of dependence, because it captures the idea that every possible influence on P was registered on S. By making measurements just on S, determining the state of S, we can in principle determine the state of space-time everywhere in the domain of dependence of S. A Cauchy slice can be thought of as all of space in a moment of time. This is the closest you get in general relativity to the idea of the Newtonian absolute space. And that's why globally hyperbolic spacetimes are the appropriate settings for the initial value formulation of general relativity. You specify appropriate initial data on a Cauchy slice, and that determines the state of the entire space-time. And the fact that the causal diamonds are compact is a beautiful paper by Minguzzi and Sanchez on causal structure, where they give a really beautiful explication of the physical meaning of this point, and they say it better than I could, so I'm just going to quote them. So the compactness of the causal diamonds can be interpreted as there are no losses of energy information in the space-time. Otherwise, one could find a sequence of points in the causal diamond with no converging subsequence. That's what it means for a set in a Hausdorff manifold not to be compact. We can take a sequence of causal curves joining the vertices of the diamond passing through our sequence of points. The limit curve, so we have this infinite sequence of causal curves entirely inside the causal diamond. There's a limit curve that starts at P, but that limit curve can't reach Q. Otherwise, R of n would have a limit. So this can be interpreted as something which is suddenly lost or created in the boundary of the space-time. That is, there's a singularity is visible from the past vertex of the causal diamond. There are naked singularities. So the fact that these causal diamonds are compact essentially rules out the existence of singularities in the middle of space-time that are visible to observers. So again, I hope this gives you a feel, but this is a lot of the game in causal structure in relativity. You try and come up with a definition that on its face seems rather abstract in its truth. All causal diamonds are compact. But you do it because you're trying to capture usually what seems like a rather simple and straightforward physical idea. There are no naked singularities. Things don't pop into and out of existence right in space-time. You can't just lose or gain energy ex nihilo or ad nihilum right in the middle of space-time. And that's exactly what this mathematical definition perfectly captures. And from this extraordinary essay that I've been stealing images, I've been stealing the figures from, they have a marvelous remark about it. They say the subject of causal structure has the curious feature that there's a seemingly endless stream of plausible sounding statements within its framework which are actually false. Frequently, these are exactly the statements one would like to have true in order to prove something interesting. In causal structure also has the curious feature that general relativistic spacetimes can be as complex and subtle as you are clever in constructing them. So something that sounds plausible, a statement about causal structure, you always immediately have to check for counterexamples to see whether the statement is just false before you even start to think about trying to prove it. And usually any plausible assignment statement you come up with will be false. And you have to carefully figure out what the counterexamples are and rule them out by refining your definition. Okay, so let's talk about asymptotic structure. Wow, I'm going really slowly here. Okay, let's try and speed up a little bit. For many problems in general relativity, so for instance, defining an isolated system, one wants to know how space-time geometry behaves infinitely far away. Often one wants to know that, in some appropriate sense, it looks like Minkowski space-time, because it's flat, geodesically completely symmetric very far away. That's kind of what, again, the intuitive notion of an isolated system is. You know, there might be a lot of crazy stuff happening right in the vicinity of the system. There's a lot of curvature, and geodesics are accelerating wildly relative to each other and twisting around, and there's magnetic fields shooting out. But as you get farther and farther and farther away, there's no more matter, there's no more curvature. Space-time settles down so that the farther and farther and farther away you look, the farther and farther away you get, the original system you're looking at begins to look just like a little point with no real distinguishable features, no real intrinsic structure. So eventually it just kind of vanishes, and you're just in flat free space when you're infinitely far away, so to speak. That's kind of the intuitive idea of an isolated system, and that's what the idea of asymptotically flat is supposed to capture, as we'll talk about now. There are various in the 1950s, especially, people really started to worry. I mean, people worried about it even before this, the idea of asymptotic. But really serious work was done in the 1950s, almost always using coordinate-based formulations. But these are unsatisfying and inadequate for many reasons, as is so often the case with coordinate-based formulations. And as is so often the case in these kinds of situations, Roger Penrose solved the problem for us. He gave us a completely invariant, non-coordinate-based characterization of what it means for space-time to be asymptotically flat. Roughly speaking, a space-time is asymptotically flat if an appropriate boundary representing points at infinity can be attached to it in a suitable way. So you essentially make infinity a real place in a manifold, so to speak. So you can actually do physics in a local way at infinity. Now, a little more precisely, but not much. I think in the interest of time, I'm not going to go through this. But if people are curious about the somewhat more precise details of what it means for space-time to be asymptotically flat, we can come back to it. But right now, the main point to take away, I'll first give some terminology. So I plus here is future null infinity. It's usually called scry because it's traditionally written with as a script I, not as a normal serif font, Latin font I. So scry plus future null infinity essentially is all the points that are infinitely far away that you can reach with by traveling arbitrarily far along a null geodesic. Space-like infinity, little I naught, is the point that you can reach by traveling infinitely far away in any direction along a space-like geodesic. It's infinitely far away spatially from every point in space-time. For technical reasons, spatial infinity is represented as a single point. Null infinity is represented as a null hypersurface. It's like the boundary of a null cone in the interior space-time that's been pushed infinitely far away. So this is just the Penrose diagram of maximally extended Schwarzschild space-time of a black hole. I'm hoping that all of you have at least seen something like this diagram before. I'll say just a few remarks about reading conformal diagrams because they are of fundamental importance in the subject, because when you learn how to draw and read a Penrose or a conformal diagram, you can convey an enormous amount of information very quickly and very simply and very easily in a way that really gets the creative and imaginative conceptual juices flowing. So a conformal diagram is such that it's a representation of the space-time, such that at every point, first, every point of the diagram. So obviously it's a two-dimensional diagram. It's supposed to represent a four-dimensional space-time. So every point in the diagram, except for spatial infinity, every point in the diagram is actually a two-sphere, represents a two-sphere. And the null cones at every point are completely uniform. They are, if you drew all the null cones here, like that's a null cone right there. They look like the null cones of Minkowski space-time. They're all uniform, even, homogeneous, isotropic. That's just an artifact of the way the diagram is drawn, because we're trying to capture the causal structure of the space-time in this diagram. What that means is that 45-degree lines, 45-degree straight lines always represent null geodesics. Time-like geodesics are curves that go from past time-like infinity to future time-like infinity, little I plus and little I minus. The points that are time-like related to every point in the interior space-time, the points you reach by traveling arbitrarily forward to the past or future along a time-like geodesic. Space-like geodesics are represented by horizontal curves. And volume, because of the way that we have manipulated the null cones to artificially make them all look Minkowskian and uniform, something else obviously had to change in the representation. And what gets wildly distorted in these diagrams is volume. So this is, let's ignore this part of the diagram, for instance, and just look at this upper right-hand part. So this is past null infinity. This is infinitely far in the past. This is future null infinity. This is infinitely far in the future. This is the interior. This is the event horizon of the Schwarzschild black hole. So remember that the black hole region we defined as the complement of the chronological past to future null infinity. So here's future null infinity. Every point in here you can connect to future null infinity by drawing a causal curve. In fact, by drawing an accelerated time-like curve. No point in here can you reach future null infinity. Once you pass through the event horizon, you're inside this region for good. So this is the chronological past of future null infinity. This is the complement of it, the set of points that you can't reach, from which you can't reach future null infinity. So this is the interior of the black hole. This is the event horizon, and this is the central singularity. And the way that volume gets distorted in this image is that if you're an observer freely falling into the black hole, so you'd be doing something like this actually, as you approach the singularity, you see space getting crushed to zero volume around you. But of course, that's not what this looks like. It looks like space is kind of opening up as you travel forward. So space-time volume is radically distorted in these diagrams. That's something that can very easily screw you up if you're not careful. So let's talk about energy conditions. Because energy conditions play a absolutely fundamental role in this field. Energy conditions are a way of attempting to control the unphysical parts of the mathematics we use to represent the physical world. We want to impose phenomenological criteria for deciding what counts as physically reasonable forms of matter. But a very important question to ask about them is whether they reflect anything about fundamental physics, or whether they really are just a kind of phenomenological generalizations that turn out to be unimaginably useful and fruitful in theoretical arguments. And they're peculiar energy conditions are peculiar in general relativity because of the fundamental importance of the derivation of deep results. So essentially, every single deep theorem in general relativity requires the assumption of an energy condition. But they lack, even though they're called energy conditions, and physicists usually talk as though they have perfectly clear physical meaning and interpretation. I actually don't think they do. They actually lack clear physical significance and interpretation in subtle and yet important ways. So I think there's actually a great deal of uncertainty about their theoretical and epistemic character, and they deserve a lot. They deserve a lot of attention, a lot more attention from philosophers of physics, I think. One of their most peculiar features is that for almost every single fundamental proposition in general relativity, the conservation of stress energy, the geodesic principle, they all admit interpretation as either a postulate or derived consequence. I can either assume them as a basic postulate, or else I can assume something else as a basic postulate and derive the statement. Energy conditions aren't like that. Almost none of them are derivable from any other fundamental proposition. You have to assume them as postulates. They're not laws of any standard construal. They're not empirical or inductive generalizations, because in fact, we think that all energy conditions we assume are promiscuously violated everywhere. So that makes it kind of funny that we assume them to prove everything. And yet, in some sense, they do seem to represent structure at a very deep level of our understanding of space-time and quantum field theories. There's something very mysterious going on here that I don't fully understand. So there are two kinds of formulations of energy conditions. There's the geometrical, which puts constraints on purely geometrical quantities, like say the Ricci tensor. And there's what I call the physical, which puts constraints on the stress energy tensor itself rather than on a geometrical quantity. Now, I'll just give you one, in the interest of time, I'll just give you one example. The null energy condition. The geometric version says that for any null vector k, its double contraction with the Ricci tensor is greater than or equal to 0. And this does have kind of a, if you really, if you really kind of squint and don't look very carefully and don't think very hard, then it kind of has a physical interpretation of saying that gravity is attractive. Null geodesics tend to converge towards each other when this is true. The physical condition, which is mathematically, if you assume the Einstein field equation, is equivalent to the geometric condition, but only if you assume the Einstein field equation. Because for any null vector, the double contraction with the stress energy tensor is greater than or equal to 0. I have no idea what that means physically. This looks like an energy density. If this were the tangent vector associated with the world line of an observer, this would be the energy density that observer naturally observes, associated with the ambient space-time stress energy. But I don't know what it means for an observer to travel a null curve, or for a photon to measure an energy density around it. So I have no idea what this means physically, and yet it's extraordinarily important in use. So it was important to get energy conditions out of the way before talking about the Einstein field equation, because as we'll see, you can't understand how the Einstein field equation operates in this arena without understanding energy conditions. So let's ask ourselves, what depends on the Einstein field equation? What do we use the Einstein field equation to prove? Well, if you read, if you just start reading physics journals and start reading papers about all kinds of things in general relativity, you will find physicists making the claim that geodesic theorems depend on the Einstein field equation, the causal hierarchy depends on it, singularity theorems, most black hole theorems, positive energy theorems, vanadium and bonding mass, conservation of matter, gravitational entropy bounds, topological censorship, cosmic censorship, Lorentzian splitting theorems, on and on and on and on. Physicists will blithely say, this theorem depends on the Einstein field equation. Well, actually, they don't. And I mean that in a very strong sense. For all of these results, which are really the deepest, most powerful, most illuminating kinds of theorems and results we have in general relativity, almost none of them depend on the Einstein field equation. And I mean that in a very strong sense. You can assume the logical negation of the Einstein field equation and these theorems still hold. The actual role of the Einstein field equation in these theorems, in theoretical relativity, is that it provides the physical interpretation of the assumptions one makes. The logical form of the arguments to prove all these theorems are assume some condition on some geometrical object, the Riemann tensor, the Ricci tensor, the Einstein tensor, and this is almost always an energy condition. 99.9% of the time it's an energy condition. Derives the theorem in a purely mathematical way, using purely mathematical argument. And then at the end, you invoke the Einstein field equation to give a physical interpretation to the geometrical condition you assumed in step 1 and to the result that you derive in step 2. That's the only role, is to give the Einstein field equation in almost all these theorems, is to give a physical interpretation to the mathematical results. There's a lovely quote here, again, from this Groch and Horowitz article. I could not more strongly urge all of you to go read this paper if you have the time and energy. It's an extraordinary paper. They say, in talking about proving singularity theorems, the classic singularity theorems of the 1960s, one would, of course, have to impose some restriction on the stress energy of matter in order to obtain any singularity theorems. For with no restrictions, Einstein's equation has no content. What do they mean by that? Well, there's a certain sense in which, if you go back to the formal statement of what I mean by a spacetime as an ordered pair consisting of a manifold and a metric, if you assume the Einstein field equation, that you just compute the Einstein tensor, you set the stress energy tensor equal to 8 pi times towards 1 over 8 pi times the Einstein tensor, and that is a space-time, that's a complete space-time. So the Einstein field equation is vacuous in the sense that every single 4-dimensional manifold with a Lorentz metric on it is, quote unquote, a solution to the Einstein field equation. Just give me the manifold, give me the metric, compute the Einstein tensor, that tells you the stress energy tensor. Every single Lorentz manifold is a solution to the Einstein field equation. So the phrase solution to the Einstein field equation is actually vacuous. It doesn't winnow out any Lorentzian manifold. The way one does that, the way one tries to cut down on the space of kind of reasonable or plausible space-time models to use in arguing is by doing things like imposing energy conditions. But this raises a very deep methodological and epistemological problem. Given the fact that so many of the results relied on in black hole physics do not depend on the Einstein field equation, but rather only on energy conditions, how much of the problems we will consider bear on the validity of GR, if at all, rather than solely on that of quantum field theory and particular theories of matter that we use quantum field theory to formulate? If almost everything in black hole physics doesn't actually depend on the Einstein field equation, except for its physical interpretation, then that, to my mind, suggests that it might be more fruitful, contrary to what a lot of physicists in the field think, especially physicists who come from a particle physics background. We might not need to change general relativity so much in order to make progress, say, in trying to think about black hole thermodynamics and solve the conceptual problems. We might need to think more about altering quantum field theory, because general relativity, in a sense, is providing only a very abstract schematic framework within which these problems and issues are being formulated. It is placing, at least by way of the Einstein field equation, it's placing very many substantive constraints on the problem by way of causal conditions, global conditions, asymptotic flatness conditions. But intrinsically, general relativity by itself is not, the Einstein field equation is not imposing any real constraints on what's going on. So since I began my lecture at around 11:06, is it okay if I continue to 12:36? I was told I should speak for about 90 minutes.
Yeah, it's up to you. So the more you talk, the less time we have for the Q&A, but it's all up to you. You can also get the whole 2 hours if you wish.
No, I don't want to do that.
Okay.
I definitely want Q&A.
Okay.
So I'll just go for 5 more minutes, get as far as I get, and pick up tomorrow, and I think I'll be able to, with all of this background behind us, I think I'll be able to go more quickly tomorrow and actually work through the information loss paradox. Not tomorrow, Wednesday, my next lecture. Work through the information loss paradox and holography arguments with all this behind us.
Yeah, that sounds fine.
Okay, good. So let's now finally start thinking about black hole mechanics and black hole thermodynamics. Start with our three best physical theories and their discontents. Well, the first of our three best theories is general relativity. Its regime of applicability, it's the regime in which we think it's a good, useful, adequate, appropriate theory. It's a regime, it's valid from middling to largest spatial and temporal scales, and from near perfect vacuum to superdense matter. It infamously postulates a dynamical space-time geometry. There are no quantum effects, in classical GR, no quantum effects whatsoever are posited or taken account of. And it admits, as we've had some suggestion, a little bit of suggestion so far, and as we'll see in Wednesday's lecture, we'll really get into some hairy details. It admits some really extreme causal and topological weirdness, which is seemingly inconsistent with a lot of the features of quantum mechanics, which lies, in many ways, this inconsistency lies at the heart of the information loss paradox. Quantum field theory, the second of our best theories, not the second best theory, but just number two in an iteration of our three best theories. It's valid for mesomolecular and smaller matter at the smallest spatial and temporal scales, and for the highest and lowest energy scales that we have access to. It assumes a static flat space-time geometry. It has no gravity, and it's important to note. This is a point that I think is often not well understood or recognized. The fact that quantum field theory assumes a static flat space-time geometry, by itself, that doesn't mean it doesn't include any contribution or representation of gravity, because that's consistent with allowing soft gravitons as part of one's model. But in standard quantum field theory, we don't consider gravitons, so there's no gravity. And then there's the extreme quantum weirdness, superpositions, probably entanglement, that kind of thing, non-locality, that is seemingly inconsistent with general relativity. And the third of our best physical theories is thermodynamics. It's really to my mind, thermodynamics is more empirically successful and deeply entrenched even than either of general relativity or quantum field theory. It's valid for all matter at ordinary spatial and temporal scales and for all masses and energies. There is no gravity and no quantum effects it takes account of. And it has built into a temporal asymmetry and the notion of irreversibility that is seemingly inconsistent with both general relativity and quantum field theory. So we have these three spectacular theories, each conceptually, but how do they fit together? Each is conceptually and physically independent of the other two. Each finds application in regimes that are well separated from those of the other. The most characteristic features of quantum field theory, superposition, entanglement, uncertainty principle, and non-locality, are in manifest tension, if not outright contradiction, with those of general relativity, chemical space-time geometry, causal weirdness, non-trivial topology. Both of them are in manifest tension, if not outright contradiction, the most characteristic features of thermodynamics, irreversibility and temporal asymmetry. So how do they fit together? I think we have to say, let's face it, we don't know how they fit together, and we don't even know whether they do in any really reasonable sense. I will say that I think at the root of many of these problems, how they all fit together, can be pinpointed in the fact that quantum theory is fundamentally a linear and general relativity fundamentally a nonlinear theory. But there's one major exception. When we say we don't know how they fit together, there's one major exception. When the effects of quantum fields are taken into account, black holes and general relativity, even though they are nothing more than regions of empty space-time, appear to become true thermodynamical objects with an associated physical temperature and entropy. This is the field of black hole thermodynamics. It's a deep and hitherto unsuspected connection among our three best, most fundamental theories. And it raises many deep philosophical problems and questions, most of which philosophers have really not yet begun to grapple with at all, and physicists neither. So there are let's think about the traditional philosophical puzzles that associate some of them, some of those, say, popular, influential, most widely treated philosophical puzzles associated with these three theories. So in general relativity, you have the nature of space-time. Are you a substantivalist or are you a relationalist? Or do you think the whole debate is silly? Is general relativity deterministic or is it indeterministic? So the whole argument in naked singularities. In quantum field theory, there's, of course, the measurement problem. There's non-locality, Bell's theorem, action at a distance. Is there a coherent ontology? In thermodynamics, we have the status of the second law. Is it an empirical generalization? Is it the law of nature? We have how to properly understand the temporal asymmetry and associated irreversibilities. We have the problem of trying to reduce thermodynamics to statistical mechanics. These are all the traditional philosophical puzzles associated with these three theories. The central problem of black hole thermodynamics, however, I claim, is what does it mean to conceive of and treat black holes in the presence of quantum fields as thermodynamical systems? You hear this claim all over the place. You can't throw a rock in the physics literature or the philosophy literature, limited as it is, without hitting the claim black holes are thermodynamical systems. What does that mean? I claim if we could figure that problem out, if we could make progress on that problem, we would have eo ipso made enormous progress on almost every other problem in the field, because every problem devolves upon and depends on this one. This problem ramifies everywhere. And I would say not only does the central problem completely ramify throughout all of black hole thermodynamics, but it's no exaggeration to say that it affects essentially every traditional philosophical problem of all three theories. It restricts and refines how they can be cogently formulated when we study these problems in the context of black hole thermodynamics. It changes the criteria for what may and may not count as satisfying answers, and it may sometimes suggest new avenues of attack. On top of that, it results in several entirely new deep problems independent of the traditional ones. So this is why I think it's so important for philosophers to study this field, because black hole thermodynamics are without a doubt the most widely accepted, most deeply trusted results in theoretical physics in which those theories work together. But as I've remarked, those theories are prima facie inconsistent, and we have no empirical access to those regimes. Absolutely no experimental or observational evidence for any of it. Why do we trust it so much? Why do theoreticians trust black hole thermodynamics so much? 99.9% of theoreticians will look at you like you're crazy if you say, I don't believe in black hole thermodynamics. I don't think there's Hawking radiation. I don't think black holes have an entropy. They'll laugh you out of the room. Why? We have no experimental or observational evidence for any of it. These investigations are necessarily speculative in a way unusual, even given that we've taken all these physical principles and all these three separate independent theories, tried to combine them in completely novel ways, and extend them into regimes to which we have no empirical access to whatsoever. That makes these investigations necessarily speculative in a way unusual, even in theoretical physics. And you find that there are technically sophisticated physical questions that are inextricable from very subtle philosophical considerations that span ontology, epistemology, and methodology, again, in a way unusual, even in theoretical physics. Black hole thermodynamics and results concerning quantum fields in the presence of strong gravitational fields more generally are without a doubt a widely accepted, most deeply trusted set of conclusions in theoretical physics, in which general relativity and quantum field theory work together seemingly in fruitful harmony. And again, I can't emphasize this enough. This is especially remarkable when one reflects on the fact that we have absolutely no experimental or observational evidence for any of it, nor hope of gaining experimental access anytime soon to the regimes where such effects may appreciably manifest themselves. If you're, if you're an old cantankerous crotchety fart like I am, and you really believe that science is about the empirical you don't have to be an empiricist to believe that. You can be a realist and still think at the end of the day, the rubber has to hit the road. We have to have some experiments. We have to have some empirical evidence, or it's not science. You might really, and I deeply believe that, you might really ask yourself, what the hell is going on here? I do ask myself that quite frequently. Not just about this, of course. I ask myself that about most facets of life that I walk throughout the world. But I especially and most vehemently ask it about this. And I will stop there and pick up the lecture on Wednesday. Thank you.
Yeah. Thank you, Erik. Now we'll begin with the Q&A. Has information. I'll keep the questions on the chat so you can pick yourself with a Q if you have a full question, with an F if you have a follow-up on the answers or the questions. And at that point, when you book yourself, I'll give you the chance to make your question to Erik. So Q&A is now open. Oh, okay, so Eugene actually wrote the whole question. You can ask it by words, so you can open your microphone and ask it.
Hello, can you hear me?
Yeah, we can hear you.
All right, hi Erik, for the talk.
Hi, Eugene.
Yeah, so I mean, this might be I'm not sure if it's like, well, I mean, I'm just gonna go ahead and ask. So you mentioned earlier that the universe is not asymptotically flat, right? It's asymptotically, I guess, the sitter. So I mean, according to our best observations. So however, the typical black hole metric is asymptotically flat. So in discussions of energy conservation and stuff like that, typically relies on like ADM formulation and stuff, and this seems to require essentially asymptotic flatness. So and the infinite R limit itself, at least that's how I'm thinking about it. So I was wondering, do you think this discounts the weight should accord to this kind of discussions, or what do you think about the way of reconciling this tension between theory and reality, so to speak?
I think so. I think that's a really interesting question, and a few things to say about it. A few things to say about the particular issue of asymptotic flatness and cosmological models, the models that we use for the actual universe, and a few general remarks about idealization in physics. So while it is true that our most widely used, most easily understood, most computationally tractable, most conceptually tractable models of black holes are asymptotically flat, it's important to realize that they are asymptotically flat at null infinity, not necessarily at spatial infinity. So that means that the ADM mass, for instance, can be defined in spacetimes that are not asymptotically flat at spatial infinity, and there are ways of generalizing the concept of an asymptotic boundary, of an asymptotic infinity that you attach to relativistic spacetime, so that you actually can make sense of attaching an asymptotic boundary to the flat or open cosmological models, the flat or open FLRW spacetimes, and their slight inhomogeneous generalizations, the Bianchi models, and the Zechariah spacetimes, and all those. So there actually are mathematically well-defined, physically pretty perspicuous ways of dealing with these problems for flat and open cosmological models. For closed models, for spatially closed ones where we think space is compact, say it has the topology of a three-sphere or of a torus, then there is a mathematically consistent way to attribute an ADM. It's zero, which you might think is perhaps a little problematic or weird or funny. And if you think that, I share your qualm. And also in these closed space-time models, there is no way whatsoever to generalize the idea of an asymptotic boundary. You just can't attach an asymptotic boundary in any reasonable way to closed cosmological models. But that doesn't necessarily mean that these asymptotically flat black hole spacetimes are not useful even in closed spacetime models. Because if you think about how we model every physical system on the planet, in the world, every physical system we ever think about and conceive of and deal with in physics, we almost always assume that it's isolated in an incredibly strong sense. We more or less assume that it's kind of the only thing in the universe. You know, if I'm doing thermodynamics and and modeling, the free energy of my tea and how it's changing as it's interacting with the air and as I'm drinking it. I don't include gravitational effects from Saturn in that model. I know that I can ignore the gravitational effects of Saturn on my thermodynamical model of my teacup. Much more I can ignore the gravitational effects of M87, 50 million light years away. So there's a sense in which implicitly I'm assuming that when I model this teacup, it's kind of alone in the universe. Maybe it's not alone in the universe, but everything else is really far away. And so the way that most physicists, I think about how these asymptotically flat models of black holes work, even in these cosmological models in which we don't have a good notion of asymptotic flatness, is you kind of think of it's related to the remark I made earlier about the fact that for all intents and purposes, for an astrophysicist, we are at eternal infinity with regard to Sagittarius A star in the middle of the galaxy. We're so far away from Sagittarius A star that any gravitational effect it has on us is utterly negligible. And space-time around us, essentially compared to the curvatures near Sagittarius A star, space-time around us is flat. So we're basically infinitely far away. Basically, space-time is flat. We're at eternal infinity. For the purposes of approximation and idealization, we can model M87 using curved space-time and just think of us as being at null infinity. So, and I claim that kind of idealization is in principle no different than that in using Newtonian gravitational theory to model the solar system while ignoring the gravitational influence of the rest of the universe. You're doing exactly the same thing there. You're basically treating the solar system as being embedded in an asymptotically flat Newtonian spacetime. So that's the practical answer. But the more difficult and problematic answer is, I think you really, really, really do need to work through the conceptual issues, because unlike the case of modeling the solar system in Newtonian gravitational theory and assuming that you're embedded in this asymptotically flat Newtonian spacetime, that everything else in the universe is infinitely far away, and so it doesn't gravitationally affect the planets, the planetary orbits in the solar system. Unlike that, we make use of this enormous wealth of theorems about black holes that essentially depend on the fact that they are exactly asymptotically flat. And it's, to my mind, not a clear question at all. It's not a clearly understood question at all how the practical idealization we use in astrophysics, we are at eternal infinity with respect to Sagittarius A star, squares with the use we make of these exact theorems that exactly depend on a real asymptotic flatness. So I think that there's a very interesting problem here that needs to be looked at.
Thanks a lot.
Okay, thank you. Now we have Curiel. Question. On you go. Well, just a second. We have a follow-up on from Manus. So I'll take the follow-up first, then we'll move to Curiel.
Okay, so can you hear me? Yeah. So you mentioned that there are no event horizons if space-time is not asymptotically flat. Is that correct? So yeah, how would...
So yeah, So how would I characterize killing horizons, black hole and cosmological horizons of Schwarzschild de Sitter spacetime? Excellent question, and I'm actually going to cover that in the next lecture. So the short answer is that by event horizon, I mean something very precise and technical. I mean the classic definition given. Actually, the history is actually really interesting. Klaus Lanzmann and I, a couple of months ago, actually spent a good 2 weeks going back to the history of the 60s and 70s, trying to figure out who actually first gave the canonical definition of event horizon. We could not figure it out. It's some combination of Penrose, Hawking, and Goroch, but at least from publications, we couldn't figure it out. Anyway, that classic standard definition relies on asymptotic flatness. There are, in fact, ways of generalizing asymptotic structure so that you can talk about asymptotically de Sitter spacetimes, asymptotically anti-de Sitter spacetimes. And there are, in those generalized asymptotic structures, there's the analog of an event horizon that we use to define what we call, say, Schwarzschild de Sitter black holes. And I'll talk about that in the next lecture.
Okay, thanks.
We move on to Curiel's question now.
Yes, thanks for the interesting talk. I have a question to your understanding of the role of the Einstein field equations in general relativity. And my wonder is whether the claim you've made goes a bit too far. So I understand that the energy conditions are obviously independent of the Einstein field equations, and also that the singularity theorems do not rely on the Einstein field equations, and also that the geodesic law, for example, does not. But say, apart from the physical interpretation, the Einstein field equations also play the instrumental role to tell us how to go from the stress energy source to the curvature of space-time. And so if, for example, you go to numerical relativists and ask and tell them, well, you don't need, you just need the Einstein field equations for the physical interpretations, I don't think they will agree. So I wonder whether you agree with this.
No, thank you. That's a good question. In fact, when I made this claim in a talk a couple of years ago at a physics conference on energy conditions and space-time theories at the University of York, and Bob Wall was in the audience. When I made this claim, he got so enraged, he actually started shouting at me. And Bob was one of my advisors, and I adore Bob. He's fantastic, just fantastic in every way. It's actually one of the proudest moments of my life that I was at. And Bob is just one of the most calm, just tempered, equable, cool human beings you'll ever meet. Nothing agitates him. So it's actually one of the proudest moments of my life that actually got him to yell at me in public. It was fantastic. So I completely, so you are absolutely right to ask this question. Physicists get very upset when I make this claim, but I don't know what to say. It's true. Just as a matter of logic and math, that relation, GAB equals TAB, plays no mathematical role in the derivation of many, if not most, not almost all of these theorems. So but one has to assume it. The difference between pure math and theoretical physics is that one has a physical interpretation of the math. And the way one gets a physical interpretation of the math for these theorems is by assuming the Einstein field equation. Now, I think it's absolutely true that no theoretical physicist works like that. That's not the way they think. They don't think, I'm going to ignore the Einstein field equation, I'm going to construct a mathematical proof, and then I'm going to come back and give everything a physical interpretation. That's not the way theoretical physicists work. When they're doing their job, when they're trying to formulate theorems, when they're trying to prove their theorems, when they're trying to think about the structures they're playing with, they never separate the physical interpretation from the mathematics. So the claim I'm making is a claim about the logical reconstruction and the conceptual structure of these theorems, not about how physicists actually operate out in the wild.
Yeah, and I do see that, but how do you want to calculate the evolution of the metric field without the Einstein field equation? So what do we have instead?
Well, I never claimed that the initial value problem was independent of the Einstein field equation. It is not independent. If you go back and look at that list of theorems, I did not include the initial value problem on that list of theorems. The initial value problem does depend on the Einstein field equation. Another result that depends on the Einstein field equation, quite interestingly, is the generalized second law. Because the form of entropy, the fact that entropy of a black hole is 1/4 of the area, that does depend on the Einstein field equation. That's one of the very, very, very few results about black holes that actually mathematically, logically depends on the Einstein field equation. So I'm not claiming nothing in GR depends on the Einstein field equation. That'd be silly. I'm claiming that a really surprisingly large number of very deep and powerful theorems don't in this strict sense that I'm talking about.
Okay, I got it now better. Thanks.
We have another question from.
Is this me? Sorry.
Yeah.
All right.
Yeah.
I'll go ahead then. Thank you very much. I like the talk a lot. I'm not that much of a specialist, so I will not ask a techie question, but I'll go for a philosophical question in this case. So I think you started and ended with a reasoning on why black holes are so important. And you said not only are they cool, they're also central to our understanding of the whole of physics, in particular, some unification questions between different fields that don't seem to perfectly unite might be answered by answering questions about black holes. And then I was wondering, are these questions important in themselves, in nature somehow, or did we build the theory so that these questions are central because black holes are so cool? That's, I think, a very real possibility in perhaps the sociology of how physics developed. I think there are precedents, historical precedents to that. So I can think of, say, salamanders. So there used to be a time in the medieval age where they thought salamanders were fireproof. And I think it was Thomas Aquinas making an argument that clearly the phlogiston theory of combustion is false because salamanders are fireproof. So clearly fire is a sort of a liquid where you can put things into. And there are some things that are not consumed by the liquid. And the Gestalt shift that happened later on, so the arrival of the phlogiston theory was a refutal of that, because they realized that fire is not a liquid, it's a process, it's something that is happening to something. So you can't have salamanders being immersed into fire, so to say. And yet we don't care much about salamanders. We don't consider this switch as a switch in terms of salamanders, although arguably those questions might have been central. Perhaps because salamanders are not quite as cool as black holes. I don't know, what do you think about this?
I think that's a fascinating question. I posted a file to the chat, first of all, that I think really illustrates quite nicely why the importance of black holes being cool to physics. But so I'll make a few minor kind of technical remarks about your question, and then talk about the broader issues. So I don't think it's quite right to say that Aquinas. No one in the Middle Ages had the slightest idea about a caloric theory of heat, or a phlogiston theory of heat, or any theory of heat. Science simply was not in anything like the epistemic methodological state to even begin to study phenomena like heat in anything like a recognizably modern scientific way. So, my guess is, well, actually, I can almost be certain that one mark of that is that people probably never actually threw salamanders in the fire to see whether they burned or not. If they just threw a salamander into the fire, they would have known they weren't fireproof. So they didn't do experiments. You know, that was one of Galileo's most fundamental innovations. He actually did the experiment. He actually went out. He didn't just reason about the world. He went out and said, "Hey, world, do you actually conform to what I think about you? Let me ask you by messing around with you. So as interesting and fascinating as I think a lot of what we call medieval science is, and as absolutely fundamentally important as it is to the development of modern science, especially, you know, the development of of a very primitive form of mechanics and calculus, you know, in the 12th to the 14th centuries in Oxford and the University of Paris, you know, culminating in the really extraordinary work of people like Nicola Rami. That's still really not modern science in the post-Galileo, post-Newtonian sense. So I think I am very wary of drawing any lesson about contemporary science by looking at case studies that predate really even Newton. I mean, even Galileo and Kepler are pretty weird. I mean, Copernicus is a total freak when you really look at them very closely. So that's the kind of minor point I want to make. But putting that aside, I think that the larger question you raised is very interesting and still stands even without using the example from the Middle Ages. So it's certainly the case that in some ways the fact that black holes were discovered in the context of gravitational physics is kind of an accident. Grace Fields, who I believe is here in the audience, has written, she's a PhD student at Oxford, studying with Jeremy Butterfield. She's written a really beautiful paper that discusses exactly this point, that given how widely analog models of gravity now stretch across almost all fields of physics, it could have been the case that what we call that the essential parts of black hole structures could have been, I think, plausibly. I mean, historical counterfactual is always a little dicey, but plausibly it could have been discovered in some other field besides gravitational physics. And if they had been, I don't know whether they would have been accorded, people would have realized how central they were to a field like general relativity. As to whether, given that they were in fact discovered in the context of gravitational physics and in general relativity in particular, do I think that there's something objective about the fact that they play such a central role, and it's not just because they're incredibly cool? I'm very torn. To lay my cards on the table, at heart, I really am something of a Peircean, Carnappian, Steinian pragmatist. And I have very little patience for the realism instrumentalism debate. And I think that your question very naturally finds its home in issues about realism, instrumentalism, and pragmatism, I would add. As a pragmatist, I want to say that it is precisely because black holes have turned out to be so extraordinarily fruitful in allowing us to understand a very, very wide and broad swath of issues. They seem to be giving us understanding across an extraordinarily wide and broad set of issues and problems across a lot of physics, that there is something objectively important about them. I would never want to say that there's something, that they have some kind of metaphysical essence that makes them more important than, you know, plasmas. But at least with regard to the way we use physics and science to understand the world, it is, in that context, it is an objective fact that they are extremely important and central.
May I follow up on that, or we don't have time?
I already have a question booked, and we're already out of time. I invite everybody who has further questions or clarifications to use the Slack platform to send their questions, and we'll try to make them get to the speakers so they'll give you feedback. So I'd rather go to the question booked by Charlotte. And that's the last question for the session.
Before Charlotte asks her question, may I make a suggestion to the organizers?
Yeah.
At several physics conferences I've been at where they use Slack, they've done something extremely useful. They've created a channel for each lecture, for each talk.
Mm-hmm.
And so people who have specific or comments on a lecture will go to that channel, ask their questions, make their comments, and you can have an entire discussion really focused on that. That won't get lost in some larger general discussion about all kinds of other things. So I've asked the organizers may want to consider making a channel for each talk so that people can ask questions, make comments, and I promise, even if that doesn't happen, if you pose a question or make a comment in Slack and make it clear that it's directed at me and this talk, I will try to answer it.
Yeah, absolutely. Okay, we will take care of it. Okay, thank you for the suggestion. Charlotte?
Yeah, thank you. Can you hear me well?
I can.
Okay, so my question is related to the first part of your talk, when you said that there are many definitions of black holes and that they all depend on different branch of physics and that they are jointly inconsistent with each other. But do you think it possible to find like one common definition of black holes that is, I think it is more a metaphysical definition of black holes, that is to define them as entities that cannot be distinguished from space-time?
So I think that this is a very important question, and it really depends. So I actually had a fairly long argument about this with David Wallace a year or two ago. Well, it was definitely more than a year ago because we were in a pub drinking lots of beers. So it was back when we could have fun doing that. And he was pushing the line, I think, that you are suggesting. And I think that if you're a realist of any kind of serious, stripe or flavor, you're going to want to do this, I think. But I don't think you have to be a realist in order to want to have a single canonical definition that really makes everything clear, that everything else rests upon and grounds reasoning. So putting aside the issue of metaphysics for a minute, because I think that one can pose the question in a metaphysically neutral way, and I usually find that to be more useful. Because once you try to answer the question initially, you can then, if you want to, start discussing metaphysics, but you don't have to. My sense is that I think it's certainly the hope of a lot of physicists, the hope of people, philosophers like David Wallace and perhaps yourself. Well, I'm not sure if you're a physicist or a philosopher, but at least of people like yourself, I suspect, that there is kind of somehow floating in the background. There is a consistent, unified, canonical, natural definition of black hole that appropriately idealized and appropriately approximated gives us the tools to kind of formulate the rough concepts that are used in all the different fields of physics. I think a lot of people have that hope. I cannot say with any certainty that that's not the case. It's just my experience as both a physicist and as a philosopher is that physics just doesn't work that way. I think most philosophers in my mind are really kind of unrepentant, even if not fully self-aware Aristotelians. Philosophers have this very, very deep need that if there's a word being used, there must be a single concept, single natural, essential, canonical concept associated with that word. And that's just not how physics works, at least not in my experience. There are generally many different ways of making a concept precise, of giving, if you like, a Carnapian explication of it. Each is useful in its own context and for its own purposes. And if you're a realist, that may mean that you think that there are many, many different kinds of related things. If you're not a realist, you may think, well, there's just a lot of different fruitful ways of talking and thinking and arguing about these kind of intuitively related things. I personally don't, I just don't feel the draw. I don't see the need. I don't understand that it's the burning desire to have a single definition for what we use a single word for.
Thank you.
Thanks, Erik, again for the lecture and the answers. And we'll meet again at 2:30 Rome time zone. Again, I invite everybody who has further questions to post them on Slack. We'll sort the channel, so we'll add sections depending on the lecture. So you will find the right place to post your question. And I guess I should enjoy everybody good lunch if you're having lunch or whatever, if you're having breakfast or dinner. And we'll meet everybody at 2:30.
And I have a final request for Enzo. Enzo,
Yes.
please go have some wonderful Italian food and an espresso afterwards for me.
Okay.
I'll think about it and enjoy it vicariously.
Okay, sure.
We can also post some photographs of what we're having for lunch on the Slack channel.
That would just be cruel.
Okay.
Okay then, see everybody later.
See you later.
And enjoy your meal.